So, lecture 25 for algebra. Including today, we have 4 more classes, and what we're going to study today are rings and fields. If there are any questions about the midterm, I'm happy to answer them, but the questions on the midterm are all pretty much questions directly from the review sheet. So let me start with rings and fields, and this actually begins back in the first chapter. So let me just review a few things. So we have a group, G, and let's say this is, we have a group. The group operation can be either multiplication or addition, and it could be commutative or not commutative. There is a convention generally in algebra that if the group, you only use the group operation of addition for an abelian group. The group operation of multiplication can be used for either abelian groups or non-abelian groups, but whenever there's a plus sign as the operation in a group, it's almost always an abelian group. So suppose we have a group G, which is an abelian group under some operation of addition. And we've seen many examples of this. The integers, or the real numbers, or the rational numbers, or the complex numbers. So these are all additive abelian groups. Also, for example, let's say m sub n of any of these, say z. So this is the additive group of 2 by 2 matrices, where you add matrices by adding their coordinates. So if that's a matrix and that's a matrix, when you add them, you just add the respective coordinates. So these are all additive abelian groups. But in each of these groups, there is also a multiplication. That is, we can multiply integers or rational, real, and complex numbers. We can multiply 2 by 2 matrices. So these additive abelian groups also have a multiplication operation. And this multiplication is associative. So xy times z is x times y z for all x, y, and z, and distributive in the following sense: x times y plus z is xy plus xz, and y plus z times x is yx plus zx. So these abelian groups under addition happen to also have on them defined a multiplication that's associative and distributive. And an abelian group that has a multiplication that is associative and distributive is called a ring. So a ring R is a set with 2 binary operations, addition and multiplication, that satisfy the following properties. First, R is an additive abelian group. Second, the multiplication is associative, and the distributive law holds. So multiplication distributes over addition. You have these x times y plus z is xy plus xz, and y plus z times x is yx plus zx. Distributive associative multiplication means xy times z is x times yz. So if you have a set where you can both add and multiply, if the addition is abelian, if you have an abelian group under addition, and if the multiplication is associative and distributes over addition, then the set is called a ring. And all of these examples I gave here, the integers, 2 by 2 matrices, rational, real, complex numbers, these are all examples of rings. Another example is there are polynomial rings. So suppose we looked at, say, z squared brackets x. So this is all polynomials with integer coefficients in z. So you learned long ago how to add and multiply polynomials. And under addition, the polynomials form an abelian group, and the multiplication is associative and distributive. So this is another example of a ring. So that R be a ring, an element E in R is a multiplicative identity if EX and XE equals X for all X in the ring. That is, if you multiply by E on the left or the right, you just get back your element. A ring does not necessarily have an identity, but some rings do. If R is a ring with an identity E, then X in R is called a unit if there exists an element Y in R such that XY and YX equal the identity. So the units are the elements which in some sense are invertible. So for example, if you take the ring of integers, the unit, the identity is just the number 1, right? 1 times anything is whatever. What are the units? X and Z is a unit if there's a Y and Z such that XY equals 1. And you can solve this equation in the integers if and only if X equals 1 or minus 1. So these are the only units in the integers. If you take your ring to be the rational numbers, the identity element is the number 1. What elements are invertible? If you take X equal P over Q, different from 0, then Y equals Q over P is another fraction, is the inverse. This is different from 0, so Q is non-zero, and P is non-zero, is the inverse. So P over Q times Q over P is 1. So But for x equals 0, 0 times x is not equal to 1 for all x. You can't multiply any number you can't multiply by 0 by anything and get 1. So the units in Q are all the non-zero numbers. Let's say Q star, which is Q with 0 removed. That is the non-zero rational numbers. What about, suppose we take R to be, so this is polynomials with real coefficients. The identity is just the constant polynomial 1, the number 1. What are the units? So suppose you have f of x in this ring. F of x is a polynomial. Suppose f of x is a unit. So you have a g of x, another polynomial, with f of x times g of x equal 1. So, of course, f of x has to be non-zero and g of x has to be non-zero. Of course, if you multiply anything by 0, you get 1. But they teach you in elementary school or wherever that the degree of the product of two polynomials is the sum of the degrees. Right? If you take a quadratic polynomial times a cubic polynomial, you get a 5th degree polynomial. And the degree of a constant function is 0. So this is the same as the degree of 1, which is 0. So I have 0 as the sum of these two non-negative integers. Two non-negative integers add up to 0 only if they're both 0. So the degree of f of x has to be 0, which means f of x is a constant, a non-zero constant. Like 3. You take the constant polynomial 3, that's a non-zero constant. It has an inverse. What's the inverse? The constant polynomial 1/3. So in this ring of polynomials with real coefficients, so the units in the polynomials with real coefficients are the non-zero constant polynomials. All of these rings we've looked at, almost the rings we just looked at, the integers, the rationals, reals, polynomials with integer or real coefficients, these are all commutative rings. We look at, say, 2x2 matrices, I don't know, real coordinates, doesn't really matter. M2 of R, M2 of Z. These are non-commutative rings. Because you've seen many times that when you multiply matrices, even 2x2 matrices, the order matters. X times Y is not necessarily equal to Y times X. So these are non-commutative rings. And what is the identity? The identity element, capital I, is the identity matrix 1, 0, 0, 1. You take 1, 0, 0, 1 times any matrix A, B, C, D, you get A, B, C, D. And if you may take A, B, C, D, and multiply it on the right by 1, 0, 0, 1, you still get A, B, C, D. So this is the identity matrix in this non-commutative ring. What are the units? Well, the units depend on whether the coefficients are integers or reals, for example. What are the units? So let's see, A, B, C, D is a unit in M2 of R if and only if it has an inverse. And we've already seen, I think, that it has an inverse if and only if let's call this element capital A. If and only if the determinant of A, which is AD minus BC, is not 0. Because suppose we let delta be this determinant, AD minus BC. Again, we've seen that ABCD inverse is equal to D over delta, A over delta, minus B over delta, C over delta, minus C over delta. Multiply this by the matrix A, you get the identity. So the units in this matrix ring are the matrices with a non-zero determinant, which you're dividing by. In M2 of Z, the units, well, you can't divide in the integers generally. The units are the matrices A, B, C, D with the determinant AD minus BC equal to plus or minus 1. Because if you start with A, B, C, D and you divide by plus or minus 1, you still have a matrix with integer entries. Okay. So that is the definition of a ring. And so, okay. So what you'll find this introductory material, the definition of a ring in the text. This is chapter 1, section 1.11 that starts on page 75. Okay. We say that so that R be a ring, a subset S contained in R is a subring of R if S is a ring under the same operations, under the operations of addition and multiplication in R. So for example, Z, the integers contained in the rational numbers, this is a ring, this is a ring, Z is a subring of Q. Q is a subring of the real numbers. The real numbers are a subring of the complex numbers. So this is a chain of subrings. We saw that if you take a matrix which is, say, a 2 by 2 matrix, A, B, C, D, but D is 0. So you look at all matrices where this coordinate in the lower left-hand corner is 0. So if you take two such matrices and you add them, you get A plus E, B plus F, 0 plus 0, D plus G. Or if you subtract them. So this set of matrices with the 0 in the lower left-hand corner is closed under addition. And see what happens if I multiply them. I get AE plus BG, AF plus BH, 0E. Oh, sorry, this is 0 here, right? 0. EF, I should make this an H. 0, 0 there, and DH here. So this also has a 0 in the lower left-hand corner. So the set of matrices that say S, this is all matrices A, B, 0, D in M2 of R, is a subring. So this set of matrices with 0 in the lower left-hand corner is closed under addition and subtraction, so it's a subgroup of this set of matrices under addition. It's closed under multiplication. That's a subring. Notice it also contains the identity, because the identity matrix, fortuitously, also has a 0 in the lower left-hand corner. When we were looking at rings, if we took, for example, the ring of rational numbers, that's a commutative ring with an identity 1, and Q star, which is the set of units in Q, is in fact all of Q except for the number 0. 0 is never a unit. So every element of Q except 0 is invertible. And what is called a field is a commutative ring, so multiplication is commutative, with an identity in which every non-zero element is invertible, is a unit. So Q, R, C, these are fields. Z is not a field because not every element has an inverse. There's no inverse of 2 because 1/2, which is the inverse of 2 in the rationals, a half is not an integer. So these are fields. Fields are very nice. In fact, if we take ZP to be the congruence classes modulo P, this is a field. It's a finite field. That is, it's a field with exactly P elements, right? What are the elements? You can take 0 plus z, 1 plus z, 2 plus z, up to p minus 1 plus z. These are the p congruence classes. That's zp. And we know if A is not congruent to 0 mod p, then there exists an integer x such that ax is congruent to 1 mod p, or we can solve this equation. So you can find the number that's, say, b. There exists a b such that a times b is congruent to 1 mod p. In terms of congruence classes, that says if you take the congruence class a plus pz and you multiply it by the congruence class b plus pz, the way we define multiplication of congruence classes, this is ab plus pz. And if AB is congruent to 1, this is 1 plus PZ. This is the identity. So this B plus PZ is A plus PZ inverse. This times this is the identity. So if you look at congruence classes modulo or prime, that forms a field, a finite field. Finite fields are infinitely important in applications everywhere. Okay. Any questions so far? Someone asked how much the midterms count as a percentage of your final grade. I'll have to go back and modify what I put up at the beginning of the semester when I had originally planned just to have one midterm in the middle of the term, and I'll let you know within a day or two. Okay. Many of the concepts from group theory extend to ring theory. For example, that G and H be groups, a function f from G to H is called a homomorphism, or maybe I'll use the letter, the Greek letter phi. From G to H is a homomorphism, is a group homomorphism. If phi of xy is phi of x times phi of y for all x and y, so if for all x and y in the group, phi of xy equals phi of x times phi of xy, this is if you have a multiplicative group. If the group were an additive group, the rule for a homomorphism would be that phi of x plus y is, let's say these are both additive groups, it's phi of x plus phi of y. So suppose we have rings that R and S be rings a function, let me just write f, from R to S is a ring homomorphism if it respects both addition and multiplication. So if f of a plus b is f of a plus f of b, and f of a times b is f of A times f of B for all elements A and B in the ring R. So a function that behaves properly with respect to addition and multiplication is a ring homomorphism. Okay. Now, remember when we had a group homomorphism, it turned out to be very valuable to look at the kernel of the homomorphism, and that was always a normal subgroup of your group G. So let's look at the kernel of a ring homomorphism. So let F from R to S be a ring homomorphism. And let's say I be the kernel of F, which is all elements X in R, such that F of X is 0. So a ring homomorphism is a group homomorphism of the additive group R. So the kernel, we know, is a normal subgroup, but R is an abelian group under addition, so every subgroup is normal. So we know that I is an additive subgroup of R, right? That is, if X and Y are in I, then f of X and f of Y are both 0. So f of X plus Y, which is f of X plus f of Y, is 0 plus 0, which is 0. But what about the multiplicative structure of this kernel? So suppose that X is in the kernel, and let's say R is any element of the ring. So f of X times R is f of X times f of R, because F is a ring homomorphism. So f of X is 0. I don't know what f of R is. It's whatever it is. But if you multiply anything by 0, you get 0. So XR is also in this kernel. So if you take any element in the kernel and you multiply not just by another element in the kernel, but in fact by any element in the ring, you get 0. What about if I multiply X on the right by X? Again, because this is a ring homomorphism, f of R, X, is f of R times f of X. That's f of R times 0. F of R times 0 is 0. So Rx is in I. So this set I is an additive abelian subgroup of the ring, and it's also closed under multiplication, not just by other elements in the kernel, but by any element in the ring. And a set with this property is called an ideal. So an ideal of a ring R is an additive subgroup of R such that for all elements X in, well, this I, for all elements X in I, and any element in the whole ring, XR is in I and RX is in I. So Let's look at an example. So suppose we have m, some positive integer. So we have the integers, and we have the congruence classes mod m. And I can define a function from z to the congruence classes mod z by f of x is the congruence class f of x plus mz. So f of x plus y is the congruence class x plus y plus mz, which is the sum of the two congruence classes x plus mz and y plus mz, which is f of x plus f of y. So this function, we've seen it before, is a group homomorphism of z as an additive abelian group. And f of xy, that's the congruence class xy plus mz, which is the product of the congruence classes x plus mz and y plus mz, which is f of x times f of y. So this is an example of a group homomorphism. What is the kernel of f? It's all x, such that f of x is the congruence class 0, 0 plus mz, or mz. So this is the set of all x, such that x plus mz equals mz, which is the set of all x, such that x is actually a multiple of m. That is, it's just mz. So this is an ideal of the ring Z. Mz, this just means all multiples of m, 0, m, 2m, 3m, and plus or minus all these. Right? For example, 2z is just the even integers. And this is certainly closed under addition. The sum of two even integers is an even integer. And if x is even and y is any integer, xy is still even. So this set of even integers is closed under multiplication by any integer. So this is a nice ideal. Let me just emphasize the fact that Zm, which is the congruence classes modulo m, is a ring. So we saw that if you take the sum of two congruence classes, a plus mz plus b plus mz, we want to define that as a plus b plus mz. This is how you add two congruence classes. And we had to show this was well defined. So we showed the following. If a plus mz equals, let's say, a prime plus mz, right? This is true if and only if a is congruent to a prime mod m, if a minus a prime is divisible by m. And suppose b plus mz is b prime plus mz, all right? So in order for this addition to be well defined, we have to show that A plus B is congruent to A prime plus B prime mod M mod M. Now, to say that A is congruent to A prime mod M, this means A is A prime plus some multiple of M. And if B is congruent to B prime mod M, that means B is equal to B prime plus some multiple, let's say L times M. So if I take A plus B, that's A prime plus KM plus B prime plus LM. That's A prime plus B prime plus K plus LM. So A plus B and A prime plus B prime, they differ just by a multiple of M. So that proves this. And similarly, I wanted to find A plus MZ times B plus MZ to be the congruence class AB plus MZ. I have to show this is well defined. But if A plus MZ is A prime plus MZ and B plus MZ is B prime plus MZ, then A is A prime plus KM and B is B prime plus LM for some integers K and L. So if I multiply AB, A is A prime plus KM and B is B prime plus LM. If I multiply this, this is A prime B prime plus A prime LM plus B prime KM plus KL M squared. This is A prime B prime plus M times A prime L plus B prime K plus KLM. This is A prime B prime plus some number, I don't know, call it like Rn. So AB is congruent to A prime B prime mod M. So this multiplication of congruence classes is also well defined. That's why the congruence classes mod M form a very, very, very nice and very important finite ring. And when the modulus M is a prime, it's not only a ring, it's a field. It's always a commutative ring with a 1 with an identity. And if P is a prime, you have a field. I guess the only case when you have a field for prime moduli. Okay, so let's continue a little bit more. So what I just talked about is the introduction of rings beginning on page 75 in chapter 1. And then we jump ahead. There's a lot more about group theory in the text, but I want to spend the next couple of days talking some more about rings. So let me try to find that. So this in the text is chapter 6. Rings, starting on page 269. So we've defined rings, we've defined fields, subrings, and ideals. So let's just recall a ring homomorphism. a function phi from a ring R to a ring S is a ring homomorphism if phi of x plus y is phi of x plus phi of y for all elements of the ring R, and phi of x times y is phi of x times phi of y for all elements x, y, and R. And sometimes you have a homomorphism of rings from the ring to itself, and a homomorphism from a ring into itself has its own special name. It's called an endomorphism. So when you're going from a ring to a ring, that's an endomorphism. So there's one there are lots of examples of rings and homomorphisms. Let me give a few more examples of rings. Suppose we consider call it f of r. This is all functions f from r to r. So this is what you study in calculus, functions of the real numbers. And you can add functions. F plus g of x is just defined to be f of x plus g of x. And f times g of x is defined to be f of x times g of x. So they form a ring. In calculus, you start off by studying C of R, which is all continuous functions f from R to R. So the continuous functions are a subring of the ring of all functions. And we have sitting in that, let me call it, say, C1 of R, all two differentiable functions. F from R to R. So for example, f of x equals x squared is in C1 of R because it has a derivative. F prime of x is 2x. So a lot of calculus is studying the rings of continuous functions and differentiable functions from R to R. And in fact, there's a lot of algebra that gets into calculus if you study more and more advanced calculus. Here's another example of and I should say that, no, what's that? Here's another example. Suppose you have, say, R is R squared brackets X. This is the polynomials, the ring of polynomials with real coefficients. R, of course, is the ring. It's actually a field of real numbers. Suppose I fix a number A, a real number A. We actually have the following evaluation map. Evaluation map. Now I'm going to prove it's a homomorphism called phi sub A. Phi sub a of a polynomial f of x is just the polynomial evaluated at evaluated at a. So this means, for example, if f of x is 2x cubed minus 5x plus 1, phi sub a of f is you just evaluate this when you let x equal a. 2 times a cubed minus 5 times a plus 1, whatever number this is. This is some real number. So you're just evaluating your polynomial at a. And so this is a function which just sends every polynomial to a real number. And that's a homomorphism. So this is f sub a, or sorry, phi sub a is a ring homomorphism. So why is that? So let's just prove this. Suppose f of x is summation, I don't know, let's say c sub I x to the I. I goes from 0 up to n. So some polynomial degree at most n. And g of x is summation d sub I x to the I. Also a polynomial with most n. So f of x plus g of x, that polynomial is summation I goes from 0 up to n, ci plus di x to the I, right? That's how they taught you to add polynomials, just add the coefficients of the variables of the same degree. So this is the polynomial f plus g. So phi sub a of f plus g is f plus g evaluated at a. That summation I goes from 0 to n, ci plus di, a to the I. This is just summation ci a to the I plus summation di a to the I. So this is phi a of f plus phi a of g. So phi a is certainly a group homomorphism under addition from polynomials to the reals when you evaluate at a. What about multiplication? So if f is summation ci x to the I, and g is summation di x to the I, what is f times g? That's a polynomial. I'll write it as summation ei x to the I goes from 0 up to n, where e sub I is the sum of, see, when you multiply out, when do you, let me use the letter k here. It's my subscript. ek x to the k, and here I'll use the subscript j. So ci x to the I, dj x to the j, multiply them, you get a polynomial with coefficients e sub k. And when do you get x to the k? You get an x to the k. See, when you multiply this out, fg is summation ci x to the I, summation dj x to the j. You multiply through and distribute, you get a sum over all possible pairs I and j, ci dj x to the I plus j, right? This times this is this. And what is the coefficient of x to the k? So this is a summation over k, something times x to the k. And what you get is you get summation ci dj when I plus j adds up to k. That's fg, right? That's how you multiply polynomials. So phi sub a of fg is summation, so that's fg evaluated at a, but this is fg. This is summation over k, summation over all I plus j equal k ci dj times a to the k. That's the sum over all k, I plus j equal k, ci dj a to the I plus j. That's just the sum over all I and j of ci a to the I dj a to the j. That's f of a times g of a, which is phi sub a of f times phi sub a of g. So that is a bit of high school algebra, which is very important, and it tells us that evaluating a polynomial is a ring homomorphism. Let's recall, if we have phi from R to S, a ring homomorphism, I, which is the kernel of phi, it's all x in R, such that phi of x is 0, is an ideal of R. It's an additive abelian subgroup, which is closed under multiplication from the right or the left. Right? And so, for example, suppose we let R be the polynomials with real coefficients, S to be R, A some real number, and phi A to be the evaluation map, where phi A of F is just F evaluated at A. So the kernel of this homomorphism, it's all F such that phi A of F is 0, which means all F such that F evaluated at A is 0. So this just means all polynomials F for which A is a root. So this ideal is the ideal of all polynomials for which this number A is a root. That's an ideal. Okay, well, I think we've just done a lot of in this introduction to rings. So maybe I will stop at this point. If there are any questions, I'm happy to answer them. If not, then we are done for the morning. I mean, rings are, it's the last topic in the course. We spend most of the time in first semester algebra learning about groups, but we will be spending these last 4 lectures today and 3 more lectures on rings and fields. And I encourage you to study the book. There's a great deal in the book about this. Okay. If there are no other questions, then we're done for the morning. Okay. Be well all.